In the previous lecture we were trying to solve this minimization problem which has all variables as 0, 1 variables. The standard problem has a minimization objective with objective function coefficients non-negative. All constraints are of the greater than or equal to type, no matter what the sign is on the left hand side or on the right hand side. Therefore, a feasible solution with all if a solution with all variables equal to 0 is feasible, then it is optimal because of the nature of the objective function. So, let us start the implicit enumeration algorithm again and try to solve this problem. So, we start with something called step 1 or iteration 1. We define say S1 as a null set, which means all variables are right now at 0. They have not been fixed to either 0 or 1. They are right now at 0. So, when all of them are 0, we have another set called a set of violated constraints, and if all variables are at 0, constraints 1 and 3 are violated. So, we just we write 1 and 3 here. It is a set comprising of the violated constraints, and then we want to get a feasible solution. So, we define another set called a set of helpful variables, and any variable which has a strictly positive coefficient in any one of the violated constraints is helpful. So, we have x1 is a helpful variable, so 1, x2 is a helpful variable, x3 is a helpful variable, x4 is helpful because it has a plus 3 here, and x5 is also helpful because of both. Now, we try to bring in feasibility by yes.
Condition like that, the helpful variable must not be in S1.
Yes, when it comes, we will define it carefully. Right now, none of the variables have been fixed to either 0 or 1. So, when we get into that situation, we will kind of redefine the set of helpful variables. We need to redefine it a little more precisely, which we will do when the right time comes. So, now among these helpful variables, we can take any one of them and try to fix it to a value 1. The important condition is a helpful variable should not already be fixed at 0 or 1, then it does not qualify. A variable that is so far not yet fixed and has is a helpful variable, but we will understand the first part once we start fixing variables. So, among these we could choose any one of them. So, let us assume we start with 5, because we try to, this is not the only way of doing it. We could fix any one of them to 1, but we would still choose variable 5 because variable x5 because let us say it has a positive coefficient in both, and perhaps the sum is the biggest. For example, variable x1 also has positive coefficients in both, but this has a larger sum. So, let us assume that we fix 5 first. So, your step 2 will have S2 equal to 5, indicating that variable x5 is fixed to 1. Now, the moment we fix variable x5, we have to find out V2. V2 is a set of violated constraints. This is feasible, this is satisfied, this is also satisfied. So, V2 becomes a null set, and the moment V2 becomes a null set, which means no constraint is violated, you have a feasible solution. So, you have a feasible solution and update that solution. So, this solution is x5 equal to 1, z equal to 19. You update, initially you will initialize, for example, z equal to infinity for a minimization problem, and because this 19 is less than the best value, you will update. Much later, when you find a feasible solution, another feasible solution, if you do so, then you will verify the objective function value of that feasible solution with that of the existing best, and if it is better, you will update, otherwise you will leave it out. So, right now we update here with x5 equal to 1 and z equal to 19. There is no T2, because T2 finds a place only when there is something in V2. So, we have got a feasible solution. Now, we need to check whether this feasible solution is optimal or whether there exists any other feasible solution with a better value, in this case a smaller value of the objective function. So, you do something called backtracking. So, you backtrack, and when you backtrack you create step 3, go back to the S, create a S3 and look at the, come from the right, always come from the right side and look at the first variable that is there from the right side, okay, which does not have a bar. That bar thing I will explain immediately. Right now 5 does not have a bar, I do not have a 5 bar, okay. So I have a 5, so 5 is the only candidate and that is the candidate on which I have to backtrack. And when I backtrack, what I do is I write this 5 as 5 bar. 5 bar implies that variable x5 is now fixed at 0. So this is fixed. Now go back to V4. Yes? Yes, this implies x5 is fixed at 0. This implies x5 is fixed at 1. This implies x5 is fixed at 0. Now go back and verify. x5 is fixed at 0. The rest of the variables have not been fixed, but they are at 0. Therefore, we have a situation where all variables are at 0, with one of them x5 fixed, other variables basically hanging and not fixed to anything, but are at 0. Now, which means once again your 1 and 3 will be violated. So 1 and 3 are violated because this is satisfied. This is satisfied, so 1 and 3 are violated. Now T4 is a set of helpful variables, and now comes, sorry, T3 is a set of helpful variables. Now 5 is not a candidate at all for a helpful variable because it has been fixed to a value. So now comes the correct definition of a helpful variable. A variable is helpful if it does not figure in the corresponding S in either way. A variable can figure in S either with a plus or a minus. Minus is the bar, okay, plus implies it is fixed at 1, bar or minus implies it is fixed at 0. Those are the only two ways it can figure in S. So all those variables that do not figure in S and have a positive coefficient in at least one of the violated constraints are helpful. So now you will go back and write 1, 2, 3, 4, all of them qualify to be helpful variables. Yes, whenever you backtrack you eliminate a certain set of solutions. We will explain that part after we solve it. We will see what exactly happens. We will solve it by taking you through a branch and bound tree also. So now 1, 2, 3, 4 are there as helpful variables. You need to choose one of them and put them into the solution. Now this x1 seems to be a very good candidate because it has a 5 plus 1. There is no hard and fast rule to choose one among this. You could choose any one. You could choose them randomly, you could choose the one that has the best contribution, you could choose the first one that appears, you could do anything. So let us assume that we take variable x1 because it has a large contribution of 5 plus 1. So we do that and your step 4 now becomes, and when you write your S4 you always have to write to the right of what you have, which means this will become 5 bar comma 4. You will not write 4 comma 5 bar, you will not write any of these and particularly the S, okay, in an order other than this order. Whenever you add something into a solution it always comes after the previous step solution. You should not do 4 and 5 bar, we will see why later. First let us complete this and then explain why and what we are doing at each stage. Now go back to V4. Now this implies that this is we decided to choose 1, so this will become 5 bar and 1. Variable x1 comes in, so it is 5 bar and 1. Sorry about this confusion, 5 bar and 1. So x1 is fixed now x5 is fixed at 0, x1 is fixed at 1. So this is satisfied, this is violated, this is satisfied. So V4 is 2 because second constraint is violated by this solution. Third constraint is also violated, right. So 1 greater than 2. So, I will have 2 comma 3. So, both are violated by this. Now, go back and prepare a set of helpful variables. Now, both 5 and 1 cannot figure in your list of helpful variables. You should only look at 2, 3 and 4. Now, 2 is helpful here. So, 2 is helpful, 3 is not helpful. 3 is not helpful because both are negative, 4 again is helpful. 4 is again helpful. Now, at this stage you can go back and put one of the helpful variables and proceed. You can do that. Proceed further, you could do that. You can try something else if you want. The algorithm allows you both. In its natural course, what you would do is you will put one of the helpful variables here and proceed as you did. But you can try this also. For example, I have a situation where I have 2 and 4 as helpful variables, 5 is already fixed at 0, 1 is fixed at 1. Now, as far as this constraint is concerned, I have 2 and 4 as helpful variables. Now, it is still alright. If I put x2 alone to 1, I may be able to get feasibility. I come back to this and let us see where I am. I have 5 is fixed at 0. So, this is also, so we need to proceed. For example, what you can try and do here is, if you are able to show that if I take a violated constraints and as far as that constraint is concerned, if I put, even if I put all the helpful variables, I do not get feasibility, then you can use the earlier result of fathoming by infeasibility. You can try that, you can try doing that at every iteration. Only thing is you lose some CPU time trying to verify. Again, there is no hard and fast rule that says this is exactly the way it is. Particularly when you write an algorithm, you have no way to see the actual numbers as they are when you run it on a computer. So, for a smaller problem you can afford to do it. Otherwise, you can have a standard routine which does this at every stage and takes you through. Sometimes it is advantageous, sometimes it is not. So, we will go through this 2 and 4. Now, the violated constraints are this. So, you can either put x2 or put x4 into the solution. Let us assume you put x2 into the solution. So, step 5 is S5 equal to 5 bar 1 2. Now, V4 V5 is 1 and 2 are fixed at 1, this is satisfied. 1 and 2 are fixed at 1, this is satisfied. 1 and 2 are fixed at 1, this is not satisfied. So, I have V5 equal to 3. Now, set of helpful variables T5 for this, already 1, 2 and 5 are in the solution. So, only 3 and 4 are available. 3 is not a helpful variable, 4 is. So, I will have 4 as a set of helpful variable. Now, at least here you can check whether putting the helpful variable to 1 can bring feasibility. Now, right now it can, because 1 and 2 are fixed at 1, which is a minus 1, putting this can bring in feasibility for this constraint. So, go ahead and do it. So, step 6 will be S6 equal to 5 bar 1, 2 and 4 V6. Now, 1, 2 and 4, 6 minus 4 2 is satisfied, 3 minus 3 0 is satisfied, correct. 1, 2 and 4 is satisfied, 1, 2 and 4 is satisfied, 1, 2 and 4 is also satisfied. So, I have a feasible solution here with this. I have a feasible solution. So, I try to find out the value of the objective function for this. So, this gives me 1, 2 and 4 is 5 plus 6, 11 plus 10, 21. So, I have a feasible solution with z equal to 21. 6 plus 5 7. So, I have a solution with z equal to 18 in this case. So, I have a solution with z equal to 18 which is better than the solution with z equal to 19. So, I update a solution with z equal to 18 which implies x1 equal to x2 equal to x4 equal to 1 and z equal to 18 I update. Now, the moment I have a feasible solution I backtrack again. So, I backtrack here. Step 7, yes 7 will be, now go back, come from the right, and the first variable which does not have a bar is the one to be backtracked. So, as you come from the right, this is the variable to be backtracked. So, I have a solution 5 bar, 1, 2 and 4 bar, that is what I have. If you look at it very carefully, your V7 will be this, because this also implies 5 bar 1 2, 4 bar implies 4 at 0. So, this is the V5 will be the same as V7. You can either substitute or straight away take it from here. So, V7 will be 3. Now, go back to this 3, there is no helpful variable. Okay. Even though there is a variable 3, there is no helpful variable. So, T7 becomes null set. Now, when the set of helpful variables becomes a null set, you again backtrack. So, this is the second reason as to why you backtrack. One is when you have a feasible solution, you backtrack. Second is when you do not have a helpful variable, you backtrack. Now, when you backtrack here to step 8, so S8 will be, now this is an interesting thing about backtracking that is going to happen. Now, you will go back and backtrack on 2. So, what you will do is 5 bar 1 2 becomes 2 bar, and once you backtrack you have to leave whatever is to the right of it. In this case you will not write this 4 bar again, you will leave whatever is to the right of it. Go back, you have consistently done this, there is only 1, so there is nothing to the right of it. Similarly, there is nothing to the right of it. So, the first time you find something to the right of it, so leave out that 4. We will see each one of this in detail as to why we are doing it after we finish solving the problem. So, V8 will be, now this is like fixing 1, this is like your 5 bar 1, because this is basically 2 at 0. So, this is 5 bar and 1. So, you will have 2 and 3 as violated constraints. So, you can go back and check also, this is satisfied, this is violated, this is violated. Now, I go back to my set of helpful variables, T8 will be, already 5, 1 and 2 are fixed, only 3 and 4 are remaining, both are not helpful here with respect to this. Okay, as far as this is concerned, both are not. As far as this is concerned, 4. Now, go back and apply the other result. Now, there is a helpful variable, putting this helpful variable to 1 under the present condition cannot bring feasibility here. Okay, or as far as this violated constraint is concerned, there is no helpful variable, which means the same. This is exactly what we had, right. This is a situation where there is a violated constraint and there is no helpful variable for that violated constraint, that is 1. But there is a helpful variable 4, putting it to 1 can bring feasibility, because I have 1 plus 3 I can, but when I put this to 1, this is definitely going to be violated. So, I can either put this, have one more iteration and then go back, or I can backtrack straight away here, because I have a violated constraint, I do not have a helpful variable for this violated constraint, therefore, I can backtrack, there is no point proceeding. So, I backtrack here. I backtrack here under the assumption that I have a violated constraint in a constraint that is violated by the present solution, and there is no helpful variable as far as that constraint is concerned. I can backtrack. Now I go back and backtrack, I do step 9. Now I come from the right, so S9 will be 5 bar and 1 bar. I leave the 2 behind, I will have 5 bar and 1 bar, yes. So your 5 bar and 1 bar is like your null set straight away. I have 1 and 3 violated, and my T9 set of helpful variables will be, I should only look at 2, 3 and 4, okay. 5 bar, 1 bar implies null set, all of them are at 0. So 1 and 3 will be violated. Now I have to look at 2, 3 and 4. So 1 and 2 is helpful, 3 is helpful, 4 is helpful. I do 2, 3 and 4. 2, 3 and 4. Now go back to this. Now I already have fixed these 2 at 0. I have 2, 3 and 4 which are here. This is violated. I may still have, I can still try and put x4 and get feasibility here. Okay, it might have other indications, but let us not worry about that. Okay. I very in principle there is a helpful variable, by putting it to 1 I can get feasibility here. So I try going to 4. So I have a step 10. S10, I can put variable x4 here. Out of 2, 3 and 4, 2 has a minus 1 here, 3 has a minus 2 here, 4 also has a minus 1 here. Maybe I tried 4. So S10 will be 5 bar, 1 bar and 4. V10, this is like fixing variable x4 to 1. This is violated, this is violated, this is satisfied. So 1 and 2 are violated. T10, I can only think in terms of 2 and 3 because 1, 4 and 5 are already fixed. So I look at 2 and 3, 2 is helpful, 3 is also helpful. Now 2 is helpful, so I can have 2 and 3 here, both are helpful. And let us assume I try to put variable x2 here. So step 11, so S11 will have 5 bar, 1 bar, 4 and 2. Yeah. Constraint, I go to constraint 1, I have 5 bar, 1 bar and 4, yes. Yes, I am sorry, I can act. Yeah. Step 9 itself I can backtrack here.
So to satisfy 3, x4 has to be 1.
No, suppose I am in step 9.
Now to satisfy 3, x4 has to be 1.
When I, no, normally what you do is, this is a very small problem. See, this is something which we have to be careful about. Let us go back to this reasoning. Now let's go to step 9 and see where we are. 5 bar and 1 bar. So violated constraints are 1 and 3. Helpful variables are 2, 3 and 4. Now the logic is, when I say 2, 3 and 4, I brought in 4 because I look only at this constraint in isolation and believe that I can bring feasibility by fixing this x4 to 1. When I do that, I do not go back and check at the other violated constraint and check that when I put x4 to 1, then by putting the rest of them I cannot get that argument you normally do not do here. It is not that the argument is incorrect, it is just that if you want to write it as an algorithm for a problem which has more variables and more constraints, at every iteration you end up spending a whole lot of time checking this. So the only thing you have to do is you have to do it very judiciously, and common sense will tell you that at any point in time look at only one constraint. do not see the impact of putting a helpful variable in a constraint through a constraint on some other one. So, normally we do not do that. That is the reason why we entered this 4. We could have backtracked. If you want to see the effect of putting x4 on this, then you could backtrack, but we normally do not do that. So, here of course you can backtrack, because the 2 helpful variables 2 and 3, I go to the first constraint, already I have x4 fixed at 1. So, by putting both the helpful variables I cannot get feasibility, therefore I backtrack. Please go back to one at a time, always constraints are handled one at a time. So, go back, by putting both the helpful variables I cannot get feasibility, because I want this 2 here, therefore I backtrack here, I backtrack. So, my step 11 will have S11 equal to 5 bar, 1 bar, 4 bar, which is again like your null set, because all of them are at 0. So, 1 and 3 will be violated. Now, go back to T11. I have only 2 and 3 available as helpful variables in the list. Both 2 and 3 qualify because they have a plus coefficient here. So, 2 and 3 are helpful, but you realize that as far as the third constraint is concerned, it is violated and it does not have any helpful variable. So, it is violated, it does not have a helpful variable, I can backtrack. So, I go back and backtrack. Now, I want to backtrack, but I cannot backtrack because I do not have a variable on which I can backtrack. Only when you have at least one variable which is fixed at 1, I backtrack. Now, all of them here are fixed at 0, so I cannot backtrack. This algorithm will terminate when no backtracking is possible. That is the termination condition. So, no backtracking is possible, the algorithm terminates. And give us the best solution that you have got is the optimal solution. So, you have z equal to 18 z equal to 18 with x1, x2 and x4 equal to 1. So, this is how this algorithm works. This is a very old algorithm. It's called Balas additive algorithm. The name of the person is Balas. It's not an apostrophe. The name of the person is Balas. So, it's a 1959 algorithm. It's called additive algorithm for 0 1. It's also called implicit enumeration algorithm for 0 1. It's called an additive algorithm. Now, the original algorithm did not, for example, provide any guidelines on when do you use the second fathoming strategy judiciously. There are many things that have been kind of kept hanging and loose. The only thing that is fixed and certain, or many things are fixed and certain, among them are the rule to backtrack. When do you backtrack is fixed, termination condition is well known, and fathoming by feasibility is obvious. When I get a feasible solution, I fathom or I backtrack. Okay, we will come back to that. Now, what is not explicitly stated is, number 1, the thing that we tried to do in step 9. If you know the problem well enough, or if you can see what is happening as you see on the board, you know that fixing x4 equal to 1 is going to have a damaging effect on some other constraint. But when you cannot see the problem when it is being solved, or when you write a code to solve this, there is no way for you to know unless you go through another subroutine which does it constraint after constraint for every variable. So, there is a trade off between the number of steps versus the time you spend in a step. There is a trade off there, and conventional wisdom tells you not to bother about more than one constraint at a time and let the algorithm handle it with increased steps. Number 2, every time, for example, here when we went here, I did move to step 11 by trying to enter something, but then we realized that we could backtrack here because putting both the helpful variables cannot provide feasibility for a violated constraint. Now that is again something which you have to decide whether you want to consciously implement it in every iteration and verify whether, take every constraint and see among the helpful variables which are helpful with respect to that constraint, try to put all those to 1 and see whether it is violated or not, and then do that. That involves some more amount of CPU time, and if you want to spend that CPU time in a step, you are welcome. Otherwise you can just leave out that second way of implicit enumeration through infeasibility, just let it take something and then automatically it will show infeasibility after 1 or 2 steps. The only disadvantage is the more you start putting them in and fixing them to 1, ultimately you have to fix them to 0 by either by backtracking. So it would involve more backtracks, more steps. So again there is a trade off between increased computational effort per step versus more number of steps in the algorithm. The third thing which has not come out very explicitly in this is, how do I choose the helpful variable to enter? Now there are many ways of doing it. The simplest way, again you have to remember all this because you should assume that you are going to write a program to solve this, not solve it on the board or on the notebook. So when you write a program to do that, then the easiest thing to do is to enter the first helpful variable and finish it. If you want to choose that helpful variable which contributes, then you need to write some more lines which would take some more time to evaluate. It would involve a sorting algorithm or trying to find the maximum in a given array, and then you may have to store the extent of helpfulness with respect to the violated constraint separately, which needs just one more vector to be created and stored and so on. Typically just take the first one and blindly put it. Or what people suggested is to have an index of helpfulness which is independent of the violated constraint. See, every helpful index set comes and that is dependent on the set of violated constraints. So what you try to do is just keep an independent index of helpfulness, which simply means just add the coefficients column wise for all the variables. So when you do that, the helpfulness for variable x1 is 5 minus 2 plus 1, which is 4. It is just an index, that is all, there is nothing special about it. The extent of helpfulness here is 5 plus 1, 6 minus 2, 4. Extent of helpfulness is minus 7 plus 3, everything turns out minus 4. This is plus 2, this is 4 plus 4, 8 plus 3, 11. Which one? The fourth one. Minus 4 minus 3 is minus 7, so again I have a minus 4. Now what you try to do is keep this index fixed. This index is independent of which iteration you are, where you are and so on. If you want a simple thumb rule to tell you which one to choose, look at this set here and identify that variable which has the maximum of these. It is just a simple guideline that would have straight away taken you to x5 in the first iteration, and x5 would have given you a feasible solution. This does not guarantee any reduction in the number of steps and so on. It's just that experience and computation will tell you that this is not a bad rule to choose. Now look at your set. Set has to be defined exactly the way it is defined. This set has to be dependent on the violated constraints. It will be different in different iterations depending on V. Only when it comes to the issue of choosing which among the helpful variable I want to put, now go back, instead of doing it constraint wise or violated constraint set wise and so on, just look at this index, and this will tell you, for example, that in general you can prefer to choose to enter x5 in compared to any of those, and you would like to enter x1 or x2 in preference to x3 or x4.
Larger problems, is there an efficient way to compute vi plus 1 in terms of vi from vi?
I think there has been considerable research since 1959 on trying to make this algorithm better and better. Okay. There has to be a method, but right now I am not aware of one which does this straight away, but there has to be, one needs to go to the literature and see.
Store something like a slackness for each constraint.
No, there are multiple ways of doing it. Again, what will happen is you can also go back and show that under certain conditions or for certain problems, certain thumb rules may work better. The bottom line is it is still a worst case complete enumeration algorithm. That is something which you cannot come out of. Depending on, for example, the nature of the constraint or the sparseness of the matrix, one could do many things, and people have done many things. The implementation that I have given is an old 1959 implementation. Lots of refinements have happened to this in terms of choosing the helpful variables. Nevertheless, even the first and the old implementation is a very good one, because all you need is just 3 vectors. If I have a problem with m constraints and n variables, all I need, S is always going to be a vector of length n, as many variables. This is as many constraints, this is as many variables. That is all you need. All you need is 2m plus n, you do not need anything more. Plus, of course, one place to store the solution, which could be another n and a number, and that is all you need, which is abysmally minimal amount of memory required to solve a problem of this kind, no matter what the size is. It is just 2n plus m, it is not more than that. Right. Now, what is this backtracking and what are we trying to do in this backtracking? That is the next thing that we need to know. What is this bar business? Why should I go from the right? Why should I leave out something to the right? Right. All these are questions that we have to look at. Well, let us look at that question. Now, what did we do? Let us try to draw what is called a branch and bound tree associated with this solution, and everything will be clear. First, we said all of them are at 0, all at 0, but not fixed. We said all at 0. Now, the first step S1 was this, was the first node which is shown there. Now, here this 5 implies x5 is fixed at 1. So, basically I am trying to branch from this on variable x5, and I say here that I have created an x5 equal to 1. The other branch could be x5 equal to 0, which I have not created right now, but I know that such a branch exists because variable x5 can take only 2 values, which is 0 or 1. So, when I branch on x5, I create 2 nodes, one which fixes x5 at 1, the other which fixes x5 at 0, and I have not written the second one. So, this is x5 equal to 1, this is your step 2 solution at the end of step 2. Now, I come to step 2, this is the solution. Now, this is feasible, and please remember that when I branch from here with x5 equal to 1 and x5 equal to 0, there are 32 possible solutions, 2 to the power n possible solutions. When I branch on a single variable, there are 16 on this side, there are 16 on the other side. Now, I have evaluated only 1 out of the 16, and because of this feasibility, I am implicitly enumerating the remaining 15, which was the question asked at that time, and the answer is here. So, I am implicitly enumerating the remaining 15 because I have got a feasible solution, and I know from my rule 1 that the moment I have a feasible solution, fixing those variables that are at 0 to 1 cannot give better solution. So, this part is fathomed. We say it is fathomed, you do not move further, you fathom by feasibility and implicitly evaluate 15 other solutions. You have already evaluated one. Now, what should I do? I cannot proceed further here because I have fathomed this. Now, I have to go on the other side. So, to go on the other side, I have to create a node with x5 equal to 0, and that is exactly what I do by putting a phi bar. A phi bar implies fixing x5 to 0, and I very conveniently do it by just going back, and then wherever I do not find an, I try to go as far back as I can and then create a branch to the right. So, I have already evaluated this node, I can create a branch to the right from this. I do not want to create because this is fathomed. So, I move one step above, create from here I can create a node. So, I create this is x5 equal to 0, this is your step 3. Now, you go to step 3, you have this phi bar. Now, your step 4 you are branching on variable x1 from here. I have already realized that I am not going to look at the left hand side anymore because there are 16 possible solutions. It turned out the first one is feasible, so the remaining 15 are implicitly enumerated. So I go back to the right and then I look at this one means I am branching on x1 equal to 1, which is my S4. I call it as S4, which is your step 4. Right now I do not branch the x1 equal to 0, I just leave it as such. Now this is what I have. Now again I go back and branch here on x2 equal to 1, which is my S5. Again I can branch on the right, which I do not do now. Now I go here and define an S6 where I am branching on x4 equal to 1. Again I can create a branch on the right, which I have not done. Now this I backtrack, I fathom by infeasibility because I do not have a helpful variable. I am sorry, I fathom by feasibility because V is a null set. Set of violated constraints is a null set, which means I have a feasible solution. I fathom by feasibility. It turns out here that out of the 5 variables, 3 variables are at 1, 2 variables are remaining, but this is already fixed at 0. So 4 variables have been fixed, there is only 1 variable that is left to be fixed. So I am implicitly evaluating only one more solution. There are 2 possible solutions from there. I have got that feasibility, so I can implicitly evaluate only one more. I have implicitly evaluated the solution with x3 equal to 1. That is the solution which I am not evaluating. So I backtrack. Whenever I backtrack, I implicitly evaluate something. So I backtrack from here. Now when I backtrack from here, what I actually do is something, but conventionally what I would have done is I go back here and I would have created this branch. That is what I would have done conventionally. I do not do that. What I do is I branch from a very convenient place. So once I backtrack, I move up. This is a place where one more branch can be created, so I just do that. So I create the branch x4 equal to 0, which is my S7. So my S7 comes here with this. Now 1 and 2 remain here because this, for this, as far as this branch is concerned, x5 equal to 0, x1 equal to 1, x2 equal to 1, x4 equal to 0, so this remains, right, no problem. 4 becomes 4 bar. Now here I fathom by infeasibility because I backtrack because of t. Whenever I backtrack because of t, I have a V and then t is a null set, I fathom by infeasibility. When V is a null set and t does not exist, I fathom by feasibility. So I fathom by infeasibility. Again I have 4 variables fixed. There are only 2 solutions possible, one of which is already this. So I implicitly evaluate one solution only through this. So I backtrack from here. Again conventionally I would like to backtrack from this because this is available and this is closer to the root of the tree, but then I do not do that. I just go back, this is where I go one step back. Now I realize I can actually branch from this. So I branch from this, I create the branch x2 equal to 0, I go to S8. Now go back to S8, I have 5 bar 1 and 2. Please look at it carefully. What did we do here? When we backtracked on 2, we left out this 4. Why do we do that? That is because you want to come from here to this. Now I have the freedom again to branch on 4 if I want. So that I get because of this. That is why you leave out this. Anything that has got a bar, when I come from the right, I backtrack on 2, I do not retain this bar, I am leaving this variable, I can look at it again. So now this would mean I am fixing only 3 because I am doing this at this level. So that is the reason why when I come back here, for example, I leave out that 4, I do not retain the 4. So anything to the right of the element that is backtracked will automatically go, which implies that you are moving one layer above and backtracking and creating an additional node. So this is your S8 which has x2 equal to 0. Now at S8 I try to I again go back and backtrack here. Now I backtrack here, which means T8 is equal to 4. I backtrack on T because which means I backtrack on I fathom on infeasibility. The logic here is putting the helpful variable cannot bring feasibility. So I backtrack with infeasibility. Now the 3 variables are fixed, 2 are remaining, 4 possible solutions. I have got one of them already. So 3 solutions I am evaluating implicitly. So now I go back and now I work backwards and then move above. I can create one more thing. So I go here and create x1 equal to 0. Now let us see how that happens. So I backtrack here, I go, this 2 goes, I put a 1 bar, and that is precisely whenever you move one level above because of the backtracking, you will leave out the bars. So the 2 will go. Now here I am fixing just 2 variables in this tree. I can fix variable x2, x4 and x3 in many ways. So I come to this, which is my S9. If you go to S9, I continue again to S10 by putting a 4. So I branch on x4. So S4 equal to 1 is what I have. Again I backtrack. So this is my S10. I again backtrack. Now here again I backtrack on infeasibility because there is a T that exists and I still backtrack, which means I am backtracking on infeasibility. Now there are 3 variables fixed, 2 are possible, x2 and x3, 4 solutions are possible. This is 1 out of the 4 possible solutions. The remaining 3 you evaluate by implicit enumeration. So I backtrack here, I go back, I can create something. So I create this x4 equal to 0 and get my S11. Now in this case what will happen is the 4 will become 4 bar, nothing will happen. When you move from a 0 1 back and then move above, one level above, you will have this. Whenever you move one level above, you will have the right hand side going. If at the same level you are backtracking, it will not happen. So S11 comes, S11 is 5 bar, 1 bar, 4 bar, x5, x1, x4. And now you realize again you backtrack, want to backtrack by infeasibility. Now 3 values are fixed, 2 variables are remaining, can be done in 4 ways, out of which one of the solution is this. So 3 more solutions you have implicitly evaluated. Now again you want to backtrack, but no backtracking is possible, therefore the algorithm terminates. So out of the 32 possible solutions, this has evaluated 11 possible solutions and the remaining 21 have been implicitly enumerated. Now the reason why you are able to do this only with 3 sets or 3 vectors is because of the order in which you backtrack. This algorithm forces you to move in a certain order. This algorithm tells you that if you choose to move in a certain order, then you do not have to store everything as independent or individual nodes. You could rather store the whole thing only as 3 different vectors and proceed. So it is a branch and bound tree, but it is a very efficient way of representing a branch and bound tree. We will look at other aspects of 0 1 in the next class.